All right, welcome back, Physics C. We're going to talk about magnetic force exerted by the magnetic field on a current carrying wire. It's kind of a mouthful. That's fine. We'll do just fine, okay? So first off, a magnetic field, okay, can exert force on a current carrying wire. And there's a couple of conditions for that to happen, okay? The first is that the wire must carry current. I mean, duh. Okay, and it must be in a magnetic field. Okay. I mean, that's kind of a given, right? I mean, that makes sense. Okay. Now, when we look at another thing that needs to be important is that the current cannot run parallel to mag field direction. The reason for this is because the current and the magnetic field are vectors in this case, and what we actually end up doing is we kind of do like I believe it's a cross product of the two vectors, and the cross product of two vectors that are parallel to each other ends up being zero. So we actually can't, if current is running parallel to magnetic field, then the angle between them is either 0 or 180, and in which case it would be 0, okay? And you're going to see that here in an equation as well, in equation form, okay? The right-hand rule is, there's a new right-hand rule. This is like a force rule. We call it the force rule, okay? And it's where you do this, okay? You take your hand, your right hand, and you have your thumb points out, your pointer finger, your index finger points forward, and then your middle finger curls. You don't need your other two fingers for this. You're just going to need to use these three fingers, okay? Okay. So this new right-hand rule has different applications than the other one, right? Because physics always has to be confusing like that. We always have to have a bunch of different rules for things, and all these different things. So this is a new right-hand rule, which is different than the other one. Okay, the index finger, okay, points in the direction of I, or the current. Okay. I remember this because index starts with an I and current is denoted with an I. Okay. Sorry, I can't get my document camera to be in a good spot. I don't know what's up with it. Okay. Your middle finger, okay, is in the direction of B field or the mag field. Last year's Physics C kids remembered this pretty easily by calling it the biddle finger, okay? The biddle finger. And then your thumb points in the direction of the force. Force by magnetic field. Okay? Or F sub B, okay? Now, so, and my Physics C kids last year remember this by thumb. Okay, so F goes right here, okay, I goes right here, and then B goes right here, okay, and these are all vectors, okay. This is your index finger, starts with an I, that's the easy way to remember it. The middle finger, B, right, we put the B at the start for the magnetic field because the magnetic field is represented by B, and then we use the thumb to get force, right? My kids called that the thumb last year. Doesn't really make a lot of sense maybe, but that's fine, okay? It helps some people to remember. Here's a good equation for you to know. For magnetic force on a current carrying wire, we use F equals I, F sub B is equal to ILB, okay, times sine theta, okay? And what does everything in this equation mean? Okay, this is the magnetic force, obviously. I is current, okay? L is the length of wire in B field, okay? And B is the magnetic field strength. Okay, sine theta, right? Sine is a trig function. Theta, specifically, is the angle between the current and B. And you should know, right, that if the angle between them is 0 or 180, if they're parallel to each other, then you should end up with 0 for the sine. So sine theta would resolve out to be 0, and then the magnetic force would be 0. Okay, so if it's running parallel to the current flow, or sorry, the current is running parallel to the magnetic field, then it would be 0 because of that sine theta right there. Okay. So you should see that theta, if theta is equal to 0 or 180, then sine theta ends up being 0, and therefore no force, okay? All right. I don't have a demo for this. I can't show it to you on the video, okay, even if I wanted to. I don't really have a way to show you this demo. I can link a video for you to look at if it helps, okay? But what you would see here is you have a aluminum wire, and it's supported by 2 springs, right? And then it passes through some box where there is magnetic field, okay? And what you would do is you could then, when you connect it to a battery maybe, okay? When you connect it to a battery, so let's say that we have out to here, there's a battery. Okay. When you have a battery connected to it, I drew it backwards, okay? Okay, positive on the left side, negative on the right side. When you have a battery connected to it, what's going to happen is you're going to notice that as the current flows through the wire, the wire is then going to be affected by magnetic field from inside the box. And what's going to end up happening is that when you run it through, okay, the wire moves down, okay, which stretches the springs. Okay. So the wire will move down and the springs will stretch out, okay? So what that means is that our force is going down, okay, because it's stretching the springs out. Another thing to consider is that really quickly, our current is having to run from the positive to the negative terminal. So our current's going from the left side of the wire to the right side, okay? There's our current. There's our current, okay? So our current is running to the right, okay? And our B field is our B force is going down. So what direction does our B field have to be going? Well, let's use our right-hand rule, okay? Our new one, okay? My thumb's gonna point down because that's where the force is going. Oh, but the current is gonna go to the right, okay? So I'm gonna have to like really bend my hand here to get there, okay? But I can flip it, and it's going to be something kind of like this, okay? My force is going down this way. My current runs that way, so then it should actually come out of the page. The B field should come out of the page, okay? Makes sense on that one? So the B field should come out of the page. Okay. Drew the connection of the battery on the diagram. We already did the force and current, right? We already figured everything else out. Direction of the magnetic field, great, okay? So here's an example that pertains to it. A 0.1 kilogram bar of mass, it's submitted by 10 Newton per meter springs. The bar is 2 meters long, and 0.5 meters of the bar passes through a magnetic field. When the current is 100 amps passes through the bar, both springs contract, okay? That helps us tell us where the force is going. What direction is the magnetic field? Well, if the springs contract, that means that the magnetic force is going directly up. Okay? And then we can figure out the direction of the current. So, magnetic force going up, okay? The magnetic field goes into the page. I'm getting that the current should flow to the right. Okay? So it should flow to the right. Okay, when the current is off, okay, when the current is off, the current's off, the bar is just kind of free hanging there. It's got 2 spring forces up out on it, 2 kx initial, and then it has the gravitational force going down, okay? When the current is turned on, okay, then that means that what's happening is the bar is being lifted up, right? So there is still spring force because it's still attached to those 2 springs, okay, 2 kx. This is going to be x final because we don't know exactly how much it's stretched by, but we know that it is now being stretched to a different distance. And then we also have gravity still, okay? But also important to consider is that since the current's on, we also now have a magnetic field force, okay, lifting, okay? So when we calculate this out, right, when we write a Newton's second law equation for this, you should know that 2kx initial is going to be equal to mg, right, because it's at equilibrium. So 2kx initial is equal to mg, okay? When the current is on, then this whole thing becomes different. It would be ILB plus 2kx final equals mg, okay? Wait a minute. We have a substitution we can make here, okay? Notice that we've got an expression for mg right here, okay? And hey, wait, mg, okay? So we're going to substitute that for mg, okay? And what we should see is that we get 2kx initial minus 2kx final equals ILB, okay? Because what's going to happen is we're going to get 2kx initial, or sorry, we're going to get ILB plus 2kx final equals ILB initial, okay? We're just substituting in there, okay? And then now we're rearranging, okay? So what we're going to do now is simplify the equation as much as we can. We want to ultimately end up with B on one side, okay? Because we're being asked the strength of the magnetic field, okay? So we'll divide by IL on one side. Another thing to consider is that we've got 2kx here and 2kxf. So 2kx initial, 2kxf. Wait a minute, and we're subtracting them. So 2kx initial, 2kxf. Wait a minute, if we're subtracting them, is there another way we can represent it? We can actually represent this as 2k delta x. Okay, that's the easiest way to do it because we don't know the exact level, we don't know exactly the length of the spring when it's not stretched, and we don't know what the length of the spring is initially, we don't know what it is finally, okay? So, but we do know the difference between the two. So this is perfectly fine. And then ILB, okay? All right, get B by itself, you end up getting B equals 2k delta x over IL. And then all you gotta do is plug everything in. 2, our spring constant is 10. Delta x is delta x here is going to be, the stretch distance, right, which is 0.02, okay? And then I, the current, it tells us is 100 amps, okay? And then it says that the length of wire in the magnetic field is 0.5. Okay. So then we can calculate it out. Okay. 2 times 10 is 20 times 0.02. I don't know that one off the top of my head, unfortunately. But this should give you, and then in the bottom right, it would be 100 times 0.5. That's about half of that would be 50. Okay. You should end up getting about 0.008 Teslas. Okay. Or, if you want to be fancy, you can say 8 milliteslas, okay? And what direction is the current in the wire? Well, we already solved it. It's to the right, okay? All right, there's that example, okay? Another thing, I'll link this video too. I don't have a video of me doing it, obviously, because I don't have the setup for it. But you have, if you have two aluminum wires hanging next to each other, okay, or if you have two wires hanging next to each other, then you'll notice that what happens is if one of them is creating a current, or if there's current running through both of them, then they can actually attract or repel each other depending on the direction of the current, okay? If the two currents move in the same direction, okay, if the two currents that you observe move in the same direction, then you would notice that the wires would attract. Okay, and you'll see that in the video that I link. They do series and parallel, so they attract or they repel depending on how they feel, right? And that's kind of the answer for part 2, is they also repel. Okay. So if they carry currents in the same direction, they attract. If they carry in opposite, they repel. Okay. What might that look like? Well, wire 1, right, is the one creating the field. Let's say that the current is going to the left. Okay. Use my right hand rule. Thumb points in the direction of the current, and fingers curl in the direction of the E field. It goes into the page on the top and out of the page on the bottom. What am I doing? I'm on autopilot right now. I am so tired. These should be dots down here. Okay. So there you go. Into the page on the top, out of the page on the bottom. Okay. Wire number 2 is going to feel this force, right? The current is also going to the left. Okay. You notice it's into the page B field. Okay. Into the page. Current is flowing, in this case, to the left. Okay. So, oh, sorry, out of the page, right? Current's going out of the page. Okay. There we go. I'm trying to get my fingers reoriented here. Okay. Out of the page, current's flowing to the right. That means your force is going in the direction, or sorry, oh my gosh. Out of the page, okay. Current is going to the left. Your force is going up. Okay. That's where your thumb's pointing. Okay. So you get force. Okay. This is the force that 1 applies to 2. Okay, I'm using that agent-object notation. In the second instance, again, the wires go the same way, have current in the same direction, both to the left. Wire 2, again, into the page above, out of the page below. Okay. Use my right-hand rule. Okay, current goes into the left. B field's going into the page, so we end up with our thumb going down, which means that there is force going to the down. Okay. If they have opposite currents, okay, let's show you how that works. If wire 1 is creating the field, okay, this one's going to the left, this one's going to the right, okay, then again, we have X's on the top. Okay. This one, right, it's got the B field coming out of the page and the current's going to the right. Okay. So B field's coming out of the page. Okay. Current is going to the right. Okay. I can't like bend my hand anymore, right? Current's coming out of the page and is going to the right, so I'd actually have to twist my hand this way. Okay, and my thumb would be pointing down. So you would notice that the force here goes down. Okay. And then for wire number 2, so if wire number 2 is creating the field, okay, then you would notice that right here, right hand rule, current goes that way, into the page below, out of the page above. Okay. At the top, current goes this way. B field comes out of the page, so force is going to go up. Okay. Okay. So you get the point, right? Those are how wires attract and repel each other. Okay. Here's a good equation that you need to know, and I say it's a good equation, but you need to know what it is. Okay. For 2 wires that are near each other that are for 2 wires that are exerting a force on each other, dependent on distance. Well, first off, one current is creating. We'll call this current 2, creating. Okay. And that is going to be B equals mu naught I, okay, I2, because we're talking about the current number 2 creating the B field, 2 pi R, okay? And there's one wire feeling force. I'll call this wire 1. Okay? And that is F equals ILB. Okay? Okay. Then, what you're going to notice, right, is that, hey, we've got a B down here, and there's a B over here. So let's substitute those. And I know this is going to look really nightmarish. F equals IL mu naught times I2, okay? This is Li1, by the way, okay? Mu naught I2 over 2 pi r, okay? And then when you simplify it just a little bit, you end up getting a little bit of a nicer looking expression that goes mu naught times I1 times I2 times L over 2 pi r, okay? There you go, okay? Okay, we have two conducting rods, each of length 3 meters and mass 0.001 kilograms. They're suspended from these long wires attached to 4 hooks. A circuit not shown creates equal currents in each rod, causing them to attract and reach equilibrium in the positions shown. So they're at equilibrium right now, which means all forces are balanced, okay? In their equilibrium position, they are 0.05 meters apart. The current in the left rod is directed into the page, okay? So this is going into the page, okay? In what direction must the current in the right rod be directed for the rods to attract as shown? Well, if they're attracting, okay, then they need to be like, they need to have the like direction. So also into page, okay, because like currents attract. Okay. All the forces that are on the rod, okay, there's quite a few of them. We have a tension force that's going up and to the left, okay. We have a gravitational force going directly to the right, okay. And we have, what did I say gravitational? We have a magnetic field force, okay. And then this is going to be gravitational force going down, okay. It has a magnetic field force there. It has to be in equilibrium, because what's going to happen is this is the rod is at equilibrium. It's not moving at all, right? Okay. So there's that. Now another thing to consider, okay, is that what's happening here, right, is that the tension force has a component that goes up and a component that goes down, right? And that upwards component should be equal to mg, okay, and that horizontal component should be equal to FB, right, if all forces are going to balance, okay? So that means that Ft, okay, or sorry, let me back up a second here, okay? That means that there is an angle up here, okay, that we can actually use to solve everything in this equation. We don't know the tension in the rope. It's not given to us, right? Can we solve for it? Yeah, maybe. Actually, probably. Oh, no, sorry, we do have mass. Can we solve for it? Yeah, we can. But it's actually easier if we don't do that. And I'll show you why. It's because the triangle that is made by the tension force, okay, right angle up here, okay, this part right here is equal to mg. This part right here is equal to the magnetic field force. This part right here is equal to the overall tension. This is your hypotenuse. This is your adjacent, and this is your opposite, okay? We need to figure out a trig function. Again, we don't know the tension in the rope, but we do know mg. We're given m and g is constant. And then the magnetic field force, we're given quite a bit of information on as well. So we're actually just going to use these two components. How can we use those two components in conjunction with each other to figure out the problem? Well, let's use trig, okay? What a bright idea. So I'm going to use trig because we know that tangent of theta, right? If we're thinking of SOHCAHTOA, TOA is O and over A. So we get F sub B is equal to mg, okay? Okay. Now what we're going to do is we're going to substitute everything in. The equation for B field, or B force that we just found, we're going to substitute that in there. Tangent theta equals that whole thing right there, mu naught times I1, I2, L over 2 pi r mg. Okay, so that's the whole expression right there. Okay. Notice that I1, I2, they have equivalent charge. Okay. Notice that the currents are the same, right? They both get 100 amps running through them. So this is really just the same thing as saying I squared. Okay. Okay. So another thing to note is that what is going to be our theta, right? What can possibly be our theta? Okay. Well, if we calculate, right? If we calculate it out, okay, or sorry, let me actually go back to this really quickly. We need to figure out what theta is going to be because we need to get I by itself, right? We can multiply by 2 pi r mg on both sides. We can divide by mu and L on the other, okay? So I'm going to multiply by the denominators on both sides. That gives me 2 pi r mg times tangent theta, okay? And then on the denominator, okay, we would have mu naught L, okay? And then, of course, you would have to square root the whole thing, okay? All right. Now, you do need to figure out what theta is, okay? Because what's going to happen, okay? Oh, theta, sorry, it's in the problem right here. It's 37, right? Theta is 37. So if we plug that in, tangent of 37, and I'm going to look at my formula sheet here because it's on here. Tangent of 37 is 3/4, okay? So I can just replace that with 3/4. So what's going to end up happening is you're going to get root 2 pi rmg, okay, 3/4, over mu naught times L. And that's a really complicated calculation, or at least it looks daunting, okay? But all you're going to do is just plug that into your calculator, and you're going to laugh at this because you're going to get exactly 25 as your answer, okay? Pretty interesting how that whole thing works out, right? Okay, well, that's all I've got for you today. All right, have fun.